Hello. Today I will be teaching you sequences and series from chapters 11, sections 1 through 7 from the Calculus Early Fundamentals 6th edition textbook. Let's start off with a quick review of sequences and series. Sequences are a set of numbers, and a series is a sum of a sequence. When a sequence is convergent, it tends toward a number as it approaches infinity. However, since a series is the sum of a sequence, when a series converges, the number produced is the sum. Two common sequences are arithmetic and geometric. Arithmetic increase linearly and geometric exponentially. Sequences and series are important because they allow us to approximate functions in a more manageable way, i.e. Taylor series. Let's do a quick refresher. Write an explicit representation of the sequence 2/3, 1/3, 1/9, 1/36, and so on. The first thing we should do is set the numerators equal to one another to try and find a common pattern. We can now rewrite the sequence as 2/3, 2 over 2 times 3, 2 over 2 times 3 times 3, 2 over 2 times 3 times 3 times 4. We now see that we have a common multiple of 2/3 in each, so we can take that out for now, and remember we will have a coefficient of 2/3 in the equation, or the representation. The sequence is now 1, 1/2, 1/6, 1/24, which we know is 1 over n factorial. As such, our function a sub n is 2/3 times 1 over n factorial. We have several tests that can be used to determine if a series converges, and you should be familiar with all of them before we begin. If you are not, please review them and then come back to work on some practice problems. I will attach a link to a sheet with all the tests. Let's do a practice problem. Determine whether the summation from n equals 1 to infinity of 3 over n squared plus 5n plus 4 converges or diverges, and find the sum if possible. Does the divergence test work? No. How about the geometric series test? No again. Since we have a factorable polynomial, why don't we try the telescoping series test? The first thing we need to do is separate the factors and solve for a and b using partial fraction decomposition, not P.F. Chang's. We find that a equals 1 and b equals -1, so we can update our formula to reflect that. Now, let's write out the terms to see if they cancel. We can see that they begin to cancel at 1/5, so we can now add the remainder of them up, getting 13 over 12. Therefore, it converges by telescoping series. We have a couple more tests up our sleeve, but one interesting thing to note is that you can use the integral test to prove the p-series test. An important thing with the p-series test is that no other terms may be in the denominator, only one term with a degree. Otherwise, use the direct or limit comparison tests. Go over the integral remainder test, since I find it one of the most difficult ones. The definition of the integral remainder test is that the error/remainder of a series is the difference of the infinite sum of a series and the partial sum of a series, where the integral from n to infinity of f of x dx takes the integral of one more nth term than the integral form n plus 1 to infinity of f of x dx. I honestly have no clue what I just said, so let's break it down. The remainder is the difference between the partial sum and the actual sum, and can be represented by the integral from n to infinity of f of x dx. N being the same number of terms in the partial sum. An important thing to note is that you must state the function is positive, decreasing, and continuous in order for the test to work. Otherwise you won't get full credit. Now, we cannot actually find the exact area because n increases by 1 every time, so we will use rectangles. You may remember when we start at the nth term, all of the rectangles are below the curve, so r is less than or equal to that integral, which is depicted in this image. But when we use n plus 1, r is greater than or equal to that integral since it is an overestimate. Therefore, we can say that r is greater than 0, since n would need to be infinity to be 0, at which point it would be the actual sum, but less than the integral from n to infinity of f of x dx. Let's do a practice problem. Approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms. Estimate the error. All we have to do is plug the formula into our calculator and solve for the sum, getting 1.198 roughly. Now, let's estimate the error. The remainder using the 10th term is less than or equal to the integral from 10 to infinity of 1 over x cubed dx, which equals the limit as b approaches infinity of negative 1/2 over x squared from b to 10, which equals 1 over 200. I know I went through that kind of fast, but all I did was integrate it to get what I got. We can also be asked to find how many terms are required to find an error within a decimal place. For example, how many terms are within 0.0005 of 1 over x cubed? We go through the same steps as above, but this time all we have to do is solve for n, which we find is greater than the square root of 1000. So the sum of the first 32 terms will be within 0.0005 of the actual sum. Some notes on the direct comparison test. When adding to the numerator or subtracting from the denominator, the fraction gets bigger, so you can use it to test for convergence. When adding to the denominator or subtracting from the numerator, the fraction gets smaller, so you can use it to test for divergence. The limit comparison test can be tricky because of the number of things you must include to get full credit. When terms can't be eliminated, take the highest degrees of the numerator and denominator for your limit comparison test. A common mistake is forgetting to state whether or not the function you are comparing it to diverges or converges, since that determines the result of the limit comparison test. Notes on comparison. When comparing trig functions, change them to their maximum value to make them easier to compare. Also, the order of function rates is logarithms are less than polynomials, which are less than powers, which are less than factorials, which are finally less than composite exponentials. If you are ever in doubt over which is greater, there is a simple test to determine which function grows faster using limits, which you can see on the slide. Let's talk about alternating series. We all know the basics of alternating series, but we must always remember to determine whether or not it is absolutely or conditionally convergent. Also, remember to state that each term is less than its prior term in order to receive full credit. This is the a sub n part, not including the negative 1 to the n. Otherwise, that will definitely skew your answer. We also have an alternating series remainder, which we found was just less than or equal to the next term if it meets the standards of the alternating series test. You can use either n or n plus 1 when determining which term is within a decimal, but be careful. When using n plus 1, you will always need to add 1 to whatever you solve for n, otherwise you will be off by 1. Remember when it says within a certain decimal that it means the next term after the one you are solving for will be less than that decimal, which makes it easy to check your work. Let's do a practice alternating series remainder problem. Approximate the sum of negative 1 to the n over n cubed within 0.002. Since this is asking for a sum, we can just simply add them up one by one in our calculator to find the solution. Since it says within, we know that we will stop once a term is less than 0.002, which is the 8th term, so the sum within 0.002 is the sum of the first 7 terms. Another way to solve this is to solve for n when a sub n is greater than 0.002, which gives us n is less than 7.93, so we know that the sum of the first 7 terms will approximate the sum to the reference decimal. I know the ratio and root tests are a little bit more straightforward than the other ones, but let's do a practice problem. Determine whether or not the summation from n equals 1 to infinity of n to the n power over n factorial converges or diverges. The first thing we need to do is take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, which is equal to the limit as n approaches infinity of n plus 1 to the power of n plus 1 over n plus 1 factorial divided by n to the n power over n factorial. We can cancel out the factorials, and we will get limit as n approaches infinity of n plus 1 to the n times n plus 1 over n plus 1 times n factorial over n to the n, which equals the limit as n approaches infinity of n plus 1 to the n over n to the n, which equals the limit as n approaches infinity of n plus 1 over n all to the power of n, which we know is equal to e, which is greater than 1. Therefore, the summation of from n equals 1 to infinity of n to the n power over n factorial diverges by the ratio test. I hope this video possibly helped answer some questions you may have had about sections 11.1 and 11.7, especially the integral remainder test and the alternating series remainder, because those are the two hardest for me. We have a worksheet posted online and a quiz if you'd like to get more practice in this area. Both of the keys are online as well.